Today we are going to start the most important concept of the theory of a small oscillation. This is actually the general theory of small oscillations. In fact, this general theory of small oscillations I will divide in basically 3 lectures. This cannot be completed only in one lecture, but I will divide this concept in 3 lectures for your convenience. In fact, in this first lecture, I would like to only introduce you the basic fundamental of general theory of a small oscillation, and in the next lecture, after this lecture, we will see the solution of the equation obtained in this lecture. That is, we will solve the eigenvalue and we will obtain the eigenvalue and eigenfunction of the problem. That is, we will solve the secular equation. And after that, in third lecture, we will see the concept of solution in terms of normal coordinates. Okay. So, first of all, we are going to develop a general theory of a small oscillation. And for this, let us consider a conservative system. And we assume that our conservative system has n degree of freedom. As you know, if the system has n degree of freedom, what does it mean? It means we will need n independent variables, or you can say n generalized coordinates to describe the configuration of this system. Okay? So let us consider that q1, q2, so on qn, these are the generalized coordinates of this conservative system. As you know that if V is the potential energy of this conservative system, then this potential energy is simply the function of the generalized coordinates. So you can simply say that potential energy of this conservative system V is equal to V of q1, q2, so on qn. It means the potential energy of the system is a function of the n generalized coordinates from q1 to qn. Why n generalized coordinate? Because we have assumed that the system has n degree of freedom, so the number of generalized coordinates will be equal to n. Okay. Now, as you know that oscillation always takes place about the equilibrium position. Okay. And we are talking about the small oscillation, so definitely the system must be provided a small displacement from the equilibrium position. So let us see this figure. In fact, if you consider that the oscillation takes place on this straight line, and this point O, whose coordinate has been shown by the symbol qi0. This qi0 is the generalized coordinate at the position O, which is actually the equilibrium position of our system. Okay. When you say that this O is the equilibrium position, it means when the system is at this point O, that is at the point qi0, net force on the system is 0. Or you may also say that in this condition, the potential energy of the system is extremum, that is either maximum or minimum or 0. Okay. Now the system is slightly displaced from this equilibrium position O to a point P. Let us consider. And this slight displacement of the system is, let us say, ui. So you can say that the coordinate or the generalized coordinate of this point P will be equal to qi0 plus ui. Okay. So corresponding to point P, the generalized coordinate is qi, and that qi will be equal to qi0 plus ui. Since qi0 is the coordinate of the equilibrium position, so this is a fixed quantity, and that's why we can treat this ui, which is actually the small displacement of our particle or the system from the equilibrium position, as the generalized coordinate. Okay. So instead of qi, we can take or we can treat this ui as a generalized coordinate. Okay. And when the system is actually disturbed from the equilibrium position or displaced to the position P and released, it performs a small oscillation about this equilibrium position. Actually, for any problem of oscillation, we have to first of all write down the equation of motion. Here, the problem may be treated on the basis of Lagrangian formulation of classical mechanics or the Hamiltonian formulation. Actually, we will adopt the technique of Lagrangian formulation for solving the problem of a small oscillation. So, actually, our aim will be to find the Lagrangian of the system, and after getting the Lagrangian of system, we will write the Lagrange equation of motion, and that equation of motion will represent the equation of motion of a small oscillation, and then we will try to solve that equation. But as I have told you, that solution will be talked about in the next lecture. Here we will only obtain the equation of motion in this present lecture. Okay. So let us see that the potential energy function V is a function of n independent variables from Q1 to Q1. So this potential energy function may be expanded in Taylor series or Taylor expansion about the equilibrium position. So when actually we will expand this potential energy function V, which is a function of Q1, Q2, so on Qn, about the equilibrium position which has been defined by Qi0, that is the equilibrium position is designated by the coordinates Qi0, Q20 and Qn0. So when this V will be expanded in Taylor series about the equilibrium position, what will be that expansion? You can say, I think you have an idea of Taylor series or Taylor expansion. So this V of Q1, Q2, Qn will be equal to V of Q10, Q20, Qn0 plus summation over I1 to n del Vi by del Qi0 Qi minus Qi0. See here, this subscript 0 actually represents the equilibrium position. So this del V by del Qi and subscript is 0, this represents the first order partial derivative of potential energy function at the equilibrium position. This 0 refers the equilibrium position. Okay, and this Qi minus Qi0 is actually the displacement of the particle from the equilibrium position. Okay, and the second term is 1 over 2 factorial summation over I1 to n summation over j1 to n and del 2V by del Qi del Qj 0 Qi minus Qi0 times Qj minus Qj0. Okay, and so on. Okay, but see, the first term in this expansion in RHS of this equation 3, this V of Q10, Q20, Qn0, this V actually represents the potential energy of the system at the equilibrium position. It means this is potential energy of our system when it is in equilibrium state. And you know that potential energy in equilibrium state is extremum. It is either minimum or maximum or stationary. So you can say that this potential energy V at the equilibrium position will be a constant, and for simplicity you can easily take this constant value of potential energy equal to 0. 0 is taken only for convenience. You may also take another constant, but 0 will be the simplest constant and the most convenient constant. So we, for simplicity, as this V or at Qy0, Q20, Qn0, that is potential energy at equilibrium position is constant. So for simplicity, we take its value equal to 0. Okay? Again, now see the second term. As you know, this del V by del Qi at 0 means at equilibrium position. And you know that this V is extremum at the equilibrium position. This is extremum. And if V is extremum, then del V by del Qi will be what? This will be definitely equal to 0. So this second term will be 0. Okay. First term is constant, which we have assumed 0, but this second term is definitely 0. We have not assumed, but it is 0 because V is extremum at the equilibrium position. Okay. So finally you can say that this V will be equal to this third term, which is 1 over 2 factorial summation I 1 to n summation j 1 to n del 2V by del Qi del Qj at equilibrium position times Qi minus Qi0 times Qj minus Qj0. Okay. In fact, in this condition, this factor del 2V by del Qi del Qj at the equilibrium position, this will be a constant. This will be a constant. Okay. And this constant is denoted by the symbol Vij. Okay. And you can see that this Qi minus Qi0 will be what? See this equation 2. Qi is equal to Qi0 plus Ui. So from here you can see that this Qi minus Qi0, this will be simply equal to Ui. And similarly, Qj minus Qj0, this will be equal to what? Qj minus Qj0, this will be equal to Uj. Okay. So making these substitutions in this equation 3 and neglecting the higher order term, what will be our result for the potential energy function? You can see this potential energy function will be then equal to 1 over 2 summation I 1 to n summation j 1 to n Vij times Ui times Uj. Okay, I think you are getting the things. As I have told you that this Vij, which is a constant, and it must be evaluated at the equilibrium position because here there is subscript 0 which refers the equilibrium position. This Vij is actually equal to del 2V del Qi del Qj, or you may also say that this is del 2V del Ui del Uj. Why? Because you know del Qi. What does it mean? This is del Qi means Qi0 plus Ui. But as you know that this Qi0 is constant, so del Qi0 will be 0 and therefore this is simply equal to del Ui. And similarly, del Qj will be equal to del Uj. So instead of this Qi and Qj, you may write Ui and Uj, and so I have told you earlier that these Ui and Uj are treated like generalized coordinates. Okay. In fact, this Vij is a symmetric tensor. You will see later on that this Vij is actually a symmetric tensor, or as you can say symmetric matrix. Okay, symmetric matrix, not tensor, but symmetric matrix. As our aim is to write the Lagrange equation of motion, and you know, for writing the Lagrange equation of motion, we have to know the Lagrangian of the system, and as Lagrangian of the system is equal to T minus V, where T is kinetic energy of the system and V is potential energy. So we have already defined the potential energy of this system So for getting the expression for Lagrangian of this system, we have to know what will be the expression for kinetic energy of this system, general expression for kinetic energy. And after finding the expression for kinetic energy, we can easily find the expression for Lagrangian of the system, and then we can write the Lagrange equation of motion, which will represent the motion equation of motion for the small oscillation. So, write the expression for kinetic energy. You know that kinetic energy in the general expression of kinetic energy in Lagrangian formulation, you have studied earlier that this is just a quadratic term in which there is a square of velocity. And this quadratic term is not written in the square form, but we write this like this. This is summation I over I, and you can also say this is I1 to n, J1 to n, you can say, okay? And half Mij Qi dot Qj dot. You know, Qi dot and Qj dot both are generalized velocity, you know. And this Mij, this coefficient, is actually at the place of mass. But don't treat directly this coefficient as a mass. Because when you say mass of the particle in classical physics, then that will be a constant. But when you write Mij, this Mij in general is not a constant. You will see just now. But as you know that this Qi dot, when you say Qi dot, that means dQi by dt. But you know that Qi is equal to Qi0 plus Ui. Okay? But when you will differentiate this Qi0, that will be equal to 0 because Qi0 is constant. And so this will be simply dUi by dt. And dUi by dt will be equal to Ui dot. So instead of this Qi dot and Qj dot, you may write Ui dot and Uj dot. Have you understand or not? Because Qa dot is equal to Ui dot and Qj dot will be equal to Uj dot. Because this Qi0 is a constant, so when it will be differentiated, that will become 0. Okay? Now, as I have told you that this coefficient Mij in this expression in general is not a constant, but in general it is a function of the generalized coordinates. So this Mij is a function of q1, q2, so on, qn. Okay? And so this Mij is since a function of n independent variables, so it also may be expanded about the equilibrium position in Taylor expansion. So when we will make the Taylor expansion of this Mij, what will be our result, you can see. In fact, I have written here only the term up to the first order. Why I have written only the term up to first order, you will see later. See. So this Mij at q1, q2, so on qn is equal to Mij at q10 to qn0 plus k summation k1 to n del Mij by del qk at 0 means at equilibrium position, times qk minus qk0 plus so on. Okay? And this can be written as Mij qi0 to qn0 plus k1 to n, summation k1 to n, and del Mij by del qk at equilibrium position. This 0 refers to the equilibrium position uk, because you know qk is equal to what? This is qk0 plus uk. Okay? Now take this uk in LHS, so this will be qk minus qk0, and that will be equal to uk. Okay, so instead of this uk minus uk0, I have written here uk. Okay, now as the expression for the kinetic energy which I have mentioned here in equation 5, already this expression is in quadratic form in terms of the coordinates ui and uj. Okay, ui and uj. Already it is in quadratic form. So when you will keep this term, this second term in the expression for mij, then the product of uij and uij dot, ui dot and uj dot with this uk dot will make the kinetic energy, the expression for kinetic energy, a term higher than quadratic. But as you know, the kinetic energy term must be quadratic in velocity, and for this second term in the expansion of this coefficient mij must be omitted. It means we must have to take this constant value mij, q1 0, q2 0, so on qn 0 in this equation 5 to keep the kinetic energy term quadratic in terms of generalized velocity. Okay, so definitely this mij should be taken as a constant factor, and that constant is represented by the symbol Tij. You can see I have mentioned these facts. I am just giving the reading which just I have explained. See here, in equation 5 the term is already quadratic in ui's. Okay, we obtain the lowest non-vanishing approximation to kinetic energy T in the quadratic form only by retaining the first term in the expansion. Only the first term. When you will take the second term, the term will not remain quadratic. Okay? So if the constant values of the function mij are denoted by Tij, then what is the kinetic energy? Then kinetic energy T will be 1 by 2 summation over I, summation over j, and you can also say this is 1 to n, this is 1 to n, Tij ui dot uj dot. Okay? And just like the Vij, this Tij is also the elements of the symmetric matrix T. Okay? Symmetric matrix. We will see these matrices when we will see the eigenvalue problem in this oscillation. Then you will see the utility of these matrices. Okay? So now we have obtained the expression for the kinetic energy of this conservative system. We have also obtained the potential energy of this conservative system. So now we can easily find what will be the Lagrangian of this conservative system. As you know, the Lagrangian L of the system is T minus V. L is T minus V. So L will be what? We will substitute the values of T and V which we have just obtained, and after substituting the values of T and V which we have obtained here, the expression for L will be what? This is 1 over 2 summation over I, j, summation over j, Tij ui dot uj dot, and minus Vij ui times uj. This is the expression for Lagrangian of our system. Okay. Now, as I have told you that we will write the equation of motion in Lagrangian form, and you know, if ui and uj are generalized coordinate, then what will be the Lagrange equation in terms of these generalized coordinate? You know, since the system is conservative, so the Lagrange equation will be d dt del L by del ui dot minus del L del ui equal to 0. Okay. Now, as we have obtained the value of Lagrangian in this equation 8, and for writing the Lagrange equation we need two partial derivatives. First one is the partial derivative of Lagrangian L with respect to ui dot, and another is the partial derivative of L with respect to ui. So now we will differentiate partially equation 8 with respect to ui dot and with respect to ui to find the values of these two partial derivatives. And after obtaining these two partial derivatives, we will simply substitute these values in equation 9, and we will get the equation of motion for this small oscillation. Okay? And let us see what will be del L by del ui dot. See here, expression for L is written in this equation. Now, for a time being, let us take I equal to j. In that condition, this expression, for Lagrangian, the first term will be what? This will be 1 over 2 summation I1 to n Tij del ui dot, and since I is equal to j, so you can treat it like ui dot square. And the derivative will be what? This will be 2 ui dot, okay? 2 ui dot. Now this 2 and this 2 will cancel out, so your result will be summation I1 to n Tij ui dot, okay? And in the second term, you know there is not ui dot or uj dot is not present, so the derivative of this second term will be 0, okay? Now, we will find del L by del ui. Now, only del L by del ui is present in the second term, so here will be actually the derivative of the first term will be actually minus, okay? Sorry, derivative of the first term will be 0, and that of the second term, since there is ui times uj, that will be written as ui square, and when ui square will be differentiated, that will be 2 ui, and this 2 and this 2 here will cancel out, and so our result will be del L by del ui equal to minus summation I1 to n Vij ui. Okay? So these are the values of del L by del ui dot and del L by del ui. Now we will substitute these two values in the Lagrange equation which I have defined in this equation 9. Okay? When you will substitute the value of del L by del ui dot, this is Tij ui dot, and that will be again differentiated with respect to t, so then that will be Tij ui double dot, because that ui dot will be again differentiated with respect to t. So you can see our expression will be summation I1 to n Tij ui double dot and plus Vij ui. Why plus? Because you can see in this Lagrange equation the second term is negative, but the value of the second partial derivative is already negative, so that minus and minus will now become plus. See here, del L by del ui is negative, so this minus minus will become plus, and our result is summation I 1 to n Tij ui double dot plus Vij ui equal to 0. Okay? Actually, as I runs from 1 to n, so this equation A is not a single equation, but for the n values of this I, this equation A represents n equations. Okay? And these n equations are to be solved for the discussion of the motion of particle, which will be a small oscillatory motion near the equilibrium position. And how we will solve this equation, that solution we will discuss in the next lecture. Okay? And there you will find a secular equation, and we will solve the eigenvalue and eigenfunction problem in the next coming lecture, and that will be very important for your examination. Okay. So the problem of general theory of a small oscillation will be completed just after the second lecture. This is one of the parts of this lecture. Okay. Thank you very much.